It's a mixture of crystalline and non-crystalline regions. That means kind of semi-crystalline polymers. And if we see where we are using the polymers mostly for using the, insulator purpose, since it has got very poor electrical conductivity characteristics. And yeah, and wait, yeah. For other things, you have studied like the physicochemical characteristics or the mechanical properties. It has got very low density, and that's the reason the weight of the material, product based on polymeric material is got very lightweight. And yeah, they will have some disadvantage like degradation issue and the decomposition temperature. You cannot use polymers for high temperature materials. So we do have a natural based polymers. That means the polymer which are obtained from the renewable resources or the animal based resources like cellulose or carbohydrate polymers like hydrogens, etc., which are widely used for some special engineering applications like drug delivery or scaffolds or kind of some membrane for filtration purpose, etc. Okay. And we do have some synthetic polymers where we are using in the day-to-day life as well as for high performance application. In the sense, some aircraft and the space technology, etc., where we use some special polymers which has excellent dynamic mechanical property in the sense like low temperature flexibility as well as high temperature flexibility, as well as it can also withstand at certain slightly higher high temperature like maybe around 450 or 500. Okay. Well, now this may be the new for you guys, composite materials. Are you aware of composite materials? Or what you know or something? No idea. Subham, do you know anything about composite materials?
So they are a combination of two materials with different properties.
Yeah. So different materials means like can I take copper and zinc? Can it be
No,
called? Yeah.
by I mean you're talking about ceramics and
Mhm.
metals.
This,
So
yeah, both are should be distinct phases. One should
yes,
be of metal, and others could be of non-metals or fibers, etc. So so fine. So do you know anything about the bonding, or they have a kind of covalent bonds or ionic bond or kind of secondary bonding? How exactly it is? Do you know anything about that? Subhang, I'm asking you. Do you know something about that? It's fine.
um,
We are mixing two distant material, and as a result, how the two materials are going to react and how they're gonna connect.
I'm not sure. So.
Okay, yeah. So that is very important. Like, so we're gonna see different terms like interfaces and how to have a very good interactions between two phases or the two distant material. Because if you do not have very good interaction, as a result, the properties will not be that great. Whatever you are targeting or the desired properties. Okay. So if you see the definition, the very layman, definition, like what is composite material? It is just mixture of two or more materials, okay, which has the distant phases. That means one can be of metals and other can be of non-metals. Non-metal means ceramics or the polymer-based material, and that could be in the form of any forms like a fiber or particulate, etc. Okay, and usually if you see the terms like two different material, that means one material called as a matrix and another phases of the material will be called as a filler. Okay, that's what it consisting of. The composite consists of a filler material and the binding material. Binding material means the matrix. Okay, and the materials only bond and will not dissolve in each other. That means they will not mix each other. Dissolve each other. Okay, and filler will be used in the very minor quantity, and the binding material matrix which will be used pretty much fine. Say for example, if you use matrix 100%, and filler could be of maximum of 10% or the 20%. Okay, uh, that combination is usually called as a composite material. And if you see the, kind of mainly types of composite material, we have a fibrous types. Okay, fibrous type means the fillers, I mean the material which are going to reinforce the matrix, the fibers in the matrix, which is called fiber-based composite. And particles, the particles can be of like kind of spherical particle or the needle or the rod, etc. So if the kind of particles which are used as a filler material in any kind of matrix, which are called as particulate reinforced matrix or the composite materials. Okay? And the composite, again, it can be classified into according to the matrix. If you use metals based matrix, it's called as a metal matrix composite. And if we use ceramics or the polymer, that is called ceramics matrix based composite material or the polymer based matrix. And yeah, for example, we have a fiberglass reinforced polyester or the epoxy matrix, which are widely used for, the application for military bulletproof, etc. Okay. So fiber reinforced plastics are the polymeric materials, and even the typical example what we use in the concrete, the civil sectors, like we use steel rod and then which are reinforced in the cement. Basically sand and cement, which are acting as a matrix there. Okay. And if you see the application of composite material, to be frank, like if you see any kind of application, none of the product has, made up of sole metals or the sole ceramics or the sole polymer-based material. Most of the products are made up of composite material. If you see any kind of product, that could be of some filler, that may be of some fibers or some particles in the form of like a spherical or the nano rod or kind of needle-based structure. Okay, where it reinforces the matrix, for improving the mechanical properties or other technical properties like kind of electrical conductivity or insulating characteristics or kind of fire resistance or the kind of. So overall, if you see the material and their kind of what kind of bond exists in each material. So this is how the table shows like ceramics, it has got ionic bonding, and then we see the polymer chains as well as the kind of ceramics. There are some sort of oxide ceramics. So those are made up of covalent bonds, and then metals made up of metallic bonds. And if you see the only polymer based material, okay, between the chains, if you see the bonding, they have got a secondary bonding interaction or the van der Waals forces. So which one has got very less energy to break, or which has very less bond energy? Straight away, compared to that of metal and metallic bond, ionic bond, and secondary bonding, which exists in polymers. So if I heat slightly above the room temperature, the secondary bonding will get break, and the structure will be dissociated. All right. So now one can define, right, what is advanced engineering materials. An advanced engineering material can be defined as any new or significantly improved material that provides a distinct advantage in the form of physical or the functional performance as compared to that of conventional materials. Okay. Example like materials which are used for suturing purpose, especially for wound closures in biomedical sectors. Okay, you might have seen, right? The stitching, whenever the wound happened, they used to stitch it right. You know how good the mechanical is done. They used to pull as much as still the sutures, the fibers will not break at all. Okay, those are made up of kind of some biocompatible polymers. Okay. And yeah, so why we are calling it as advanced engineering material, because see, it has got excellent mechanical properties as well as they are biocompatible and biodegradable. Okay, over the period of time, the wound, once it is regenerated, the wound which was happened. The meanwhile, the suture material, the fibers, whatever they use, they get degraded as well as they are compatible with the living cells. Okay. As a result, your wound will be regenerated completely as well as in a very faster manner. On the other hand, yeah, you might have seen in the aircraft cabinet, which are used for, various purpose. Like it is made up of like kind of composite material, polymer-based composite material. Okay, and it is used in the different temperature. Like once it is in the, kind of, once the which is in the running condition like aircraft, like they are in the temperature of -70 also. And once it is landed, like they experience the temperature of even 35 degrees to 50 degrees. So they're kind of like different temperatures can also be, the materials can be used actually. So in the road temperature also, they should not get, damaged or kind of the flexibility, they cannot compromise. All these things will be, kind of given by this kind of advanced engineering materials. And now we will move into the composite materials. Okay. If you see the composite materials, most of the materials are polymer based matrix. So what I'm thinking, just have some basics, and so that you'll not get confused the moment when I expand some sort of like a scaffold or some membranes, etc. So why we use copolymer, or why we use some sort of carbohydrate polymers, etc. So you don't get confused. So you just have some basics, and then yeah, maybe from the next class I'll start to teach the fabrication technique as well as different applications. I mean the case studies. Okay. So you might have seen polymers, and you have studied in third semester, like polymers are widely used in the day-to-day life. Mostly they are because of they are strong, and of course they are biocompatible, and they are dynamic in nature. That means they are flexible in low temperature as well as in the high temperature applications. And yeah, if you see their application, they are used in the commercial to the high performance sectors like mechanical gear and food packaging, and in the biomedical sectors like drug delivery, scaffold, etc. And yeah, if you see the high performance application, you might have seen or you might have heard the Kevlar based fiber, which are made up of aramid fiber or nylon based polymer. The fiber made from the nylon polymer. If you see the mechanical properties, even they're even stronger than the stainless steel. Okay, the Kevlar is widely used for bulletproof. Okay, and the main key features of polymers, yeah, they are very low density. As a result, the product will be very lightweight, and they've got excellent dynamic mechanical properties, which can be used in low temperature applications. Of course, the proper fabrication or the processing of polymer is pretty easy. Okay. It is going to take very less minute. You never know. You have seen it, and I don't know. Within a 2-3 second, one polymer based product can be, prepared. Okay. The cycle time is pretty very less, like a maximum of like 1 minute or 2 minutes, you can get, number of products. And yeah, they are very cheap, and they do have some disadvantage like a degradation issue, and creep-based materials cannot be used because polymer molecules start to relax over the period of time or the temperature. Okay, so as a result, if you want to use creep-based applications with the help of polymers, then polymer is not the best choice. And yeah, the waste disposal. Yeah, if you don't know how to use polymers, that means you are harming, harming the planet for your futures. Okay. So you must know, or you should know actually where to use polymer. Means it's not the straight away, just like they're using plastics or the polymer. That doesn't look, that doesn't make sense. So yeah, polymers, they are macromolecules, and many monomers are linked together by a covalent bonds to form a very long chain, or the very high molecule which has highly entangled. So I usually look at polymer as a frozen noodles. Okay, you cannot pull out each single strands from the polymer, noodles. Okay, that means they are highly entangled each other. But yeah, of course, if you put these noodles in the boiled water, the strands will come out easily from the frozen noodle. That means slightly, once you are heating the polymer slightly above the room temperature, that means you are breaking those van der Waals bond or the secondary bonding. Okay, so as a result, the bonding between the two polymer chains will be dissociated. As a result, the polymer chains start to move, and yeah, so that is how the processing usually happens. Okay. So this is how the synthesis protocol, like you take one monomer and then you choose some polymerization technique, catalyst, etc., different temperature or the particular pressures, etc. And many monomers are combined, and it forms a macromolecule. So that is called as a polymer, or the macromolecule. So we have a typical example like ethylene is getting polymerized, and then you're getting polyethylene, and the polyethylene oxide is getting polymerized, and then you get polyethylene oxide. And do you know what is polar and non-polar polymer? No idea? Okay. So we have a classification of polymers. Polymers are classified into three major categories like thermoset, thermoplastics, elastomers. So based upon the cross-linking type or the type of curing system. If you see the thermoset polymer, they are completely cured. And if you see thermoplastic, they are not at all cured. And elastomers, they are in between thermoset and the thermoplastic. That means slightly cured. Okay. And again, thermoplastics are classified into two categories like crystalline and amorphous. Well, thermoplastic polymers, okay? If you see the definition, of thermoplastic polymers, they get softened the moment when you heat the thermoplastic polymers, and they starts to flow, once you are increasing the temperature. That means there is no cross-link between the chains, okay? Or the science aspect, like there is weak van der Waals or the attractive forces between the chains usually happen, and which can be broken by slightly warming of the thermoplastic polymers. That means the plastics, thermoplastic polymers can be recycled or remolded at any times, number of times, okay? And the commercial example, the typical example, you have a frozen butter, right, which usually take from the refrigerator, and it is usually in the form of solid form, okay, the frozen butter. And if you put them on the hot plate or the pan, they starts to melt. And it transforms into liquid. Okay, and you collect those liquids. Buttery liquid, and then you put it back in the refrigerator. Again, it transforms into solid. Okay, so that is how thermoplastic. You can melt it, and then it forms a liquid, or you can give a permanent shape. Again, if you don't like the product, you can melt it back. Again, you can change that. Shape, geometry of the product, or the shape of the product, etc. Okay? That means you can do multiple recycling or the remolding. Okay? A typical example like polypropylene-based cans and PET bottles and the carry bag which we use in the day-to-day life. And now the thermoset polymers, they are opposite to that of thermoplastic polymer. That means thermoset-based polymer has got excellent cross-linking between the chains. You can see here we have a number of polymer chains, and each chains are connected by the small bonds or some organic molecules. Okay? That means they are acting as a cross-linking, okay, between the polymer chain. As a result, even you do the, even if you heat them or if you give some mechanical forces, the chain will not move at all, okay? So rather moving between the chains, movement of chains. So once you are, rising the temperature, rather moving, they start to, kind of fuse each other, okay? That means straight away they will start to degrade, altogether. So that's called the moment when you overheat the thermoset-based polymer, they start to decompose and it cannot be remolded or reformed. That means once you are manufactured, that means done. You cannot do anything. The best one is, how you make omelette. Okay, you are going to use egg and then you are putting on the hot pan and then you get the omelette. Okay, and the omelette cannot be, you cannot get it back to the egg. The liquid form. Okay. The same cases apply for the thermoset polymers. So they are fabricating different thermoset product like a bakelite, which are, phenol formaldehyde based resins for manufacturing these kind of switches, other tires, and the polyurethane based mattress, etc. So once you have manufactured, that means you have done all this cross linking. That means if not, get it back those, the original polymers how it was. The recycling thing is zero. So elastomers, which are intermediate between thermoset and thermoplastic polymers, and they are slightly cross-linked to give those kind of permanent shape for the product. Because if you don't cross-link, the elastomers or the rubbers, they start to move, each other. As a result, whatever the geometry or the shape of the product you have planned, that is not going to, resist forever. So elastomers usually they undergo extensive elastic deformation. That means it can stretch more than 200%, and if you leave the pose, they retract rapidly. So the rubber bands which are used in the day-to-day life, which are made up of natural rubber, and the gloves based on this kind of natural rubber, which has got excellent acid resistance or the chemical resistance. And we do have some molecular structures like linear polymers, branched polymers, frosting polymers, and network structure. That means like a replication of DNA, including the double helix or triple helix based structure. So, the structure, defines various properties. That is what in the content I was telling, studying of structure property relationship. So we'll see different case studies and the structure and their properties. But nevertheless, if we try to have some fundamental like what is linear and what is branch and what is network and what is crossing structure. Of course, linear means the polymer chains which are completely straight. There is no branching side chains present in the polymer backbone. And yeah, branch means you have a polymer main chains. On top of that, you can see the side chains. I mean, some sort of like some other linkage made up of some functional groups that are present in the main chain. Okay, so those are called as some branched polymers. And cross-linked means all the chains are linked together with the, the another polymer chains with the help of either curing system or some other kind of cross-linking agents, etc. And network polymers are the DNA, based mimicking polymeric structure means they are mimicking the DNA of our living organs, like maybe in the form of double helix or triple helix. Which are widely used for biomedical sectors like drug delivery or the scaffold for tissue regeneration, etc. Okay. I can take till 10:05, right? Hello. You have a class at 10:15, right?
Yes, I are.
Okay. So this is how the macroscopy looks like this, of like amorphous polymers and crystalline polymers. To be frank, there is no material or the polymers which has like 100% crystalline or the 100% amorphous. Okay, if we see any material or the metals or ceramics, even polymers, they do have some sort of randomness or the amorphous region, and they do have some sort of crystalline region. Okay, so why? Because none of the fabrication process are like so ideal that they can fabricate completely crystalline material, maybe a metal or the polymer. Okay. So crystalline polymer means you can say like most dominant structure is crystalline region. Like kind of if you see this microscopy, microstructure, and most of the the content occupies the crystalline region. So we can call something like crystalline polymer. Okay. Say, for example, if your crystalline region, if the content is more than 80%, that those are called as a linear polymers. And if you see the polymer which has like a 50-50 or 60-40, crystalline is 60 and amorphous is 40, means kind of you should call it them as a semi-crystalline polymer. By the way, how do you analyze this? 50% or 60%, how do you analyze them? Bharatwaj, any idea? You have studied, right? Material characterization. Do you remember any techniques where we can study the percentage content of crystalline and amorphous? So you do the homework. Maybe next class we can discuss. You try to find out what are the characterization techniques to find out those kind of amorphosity or the percentage amorphous content or the crystalline content in the materials. Well, if you see the crystalline polymer or linear, usually the linear polymers are called as a crystalline polymers. Okay, and the polymer chains are packed in a regular manner, and they have got a regular chain structure. That means there is no bulky side group like a benzene or some aromatic structure present in the main chain. Okay? Since they are more crystalline, they possess more stronger and less flexibility. The best example is high density polyethylene and polyurethane based polymer. Okay? Once the density is high, that means they have got more crystalline nature. Okay. And amorphous polymers, they are usually of branched polymers. That means the polymer chains are irregularly packed or the disordered manner. And if you see their main chain, they are made up of like kind of bulky benzene group or aromatic based group, as well as the side group also exists this kind of aromatic structure. As a result, they induce more of like amorphosity in the material. And if you see the amorphous material, they got a very less stronger, mechanical property. And but on the other hand, if you see their optical characteristics, like they've got excellent transparency, and that's the reason it has been widely used in the optical applications for manufacturing contact lenses, etc. So what is cross-linking or sometimes cross-linking is also called as a vulcanization, and why it is so important? if the elastomer or the polymer which is not cross-linked, that means the chains will start to slip each other, even if they are physically entangled. Okay, the example rubber which are highly amorphous. Okay? That means if you do the permanent shape for your product, I mean, even after giving that, shape, permanent shape, over the period of time, I mean, they experience different mechanical forces as well as the temperature. So as a result, the chains will start to slip each other, and the result, the geometry will be, changed. So that's the reason we introduce some sort of bridging between the two polymer chains, okay, to make, make sure that they should not slip each other, the polymer chains. So the chemical bond linking two chains of polymers at some point rather than at the ends. Okay, that means we are introducing this bridges between the chains, not at the ends. Okay? Of course, the number of bridges or the cross-links per unit length of a polymer defines how much the degree of cross-linking, okay, or the cross-link density. So the rigidity or the strength of the polymer system increases with the increasing the cross-link density. Okay? The more the crossing density, more will be the mechanical strength or the mechanical properties. And if we see the types of cross-linking or the example for cross-linking material for the rubber formulations like sulfur, metal oxide, and phenolic-based molecules, where you can use as a vulcanization agent or the cross-linking agent. You can see here you have a mixture of polymer entangled chains, and then they are bridging some of the chains. Okay. And if you do some sort of slightly less cross-linking to the material, that is called less cross-linking. And if you do more amount of cross-linking, that is called as higher cross-linking. That leads to the higher mechanical property. So this you have studied toxicity. I'm sure everybody knows. So I'll skip this one. And yeah, this also you must be knowing homopolymer. What is copolymer? So what is alternative copolymer? Can someone tell me? Bharatwaj, what is alternative copolymers? I'm not hearing you. You are trying to speak, but
So,
yeah,
can you
please
hear?
go. Yeah.
Sir, alternating copolymers. Sir, is that what you asked? Hello?
Yeah, please go ahead.
Sir, I'm not too sure, sir. Like,
Okay. What is copolymer? Fine. What is copolymer first?
so copolymers basically when there are two or more different polymeric chains that are into this thing. For example, like ABS is there, or something like the styrene butadiene copolymer. Like basically two different polymer compounds that are together arranged in a particular manner.
Yeah, slightly fine, but not the two polymer chains. See, what is copolymer? It is a combination of two different monomer. They react each other and it forms a big macromolecule, which are made up of two different monomers. That is what it is called as a copolymer. That means two different monomer, not the two different polymer chains. Okay. Are you getting me now, Bharatwaj?
Yes, sir, I understood.
Yeah. So homopolymer means only one monomer usually participate in the polymerization technique or the reactions. Okay. Copolymer means at least two different types of monomer usually participate for the polymerization reaction and can differ in the way of monomers. Which they are arranged actually. You can see here. Homopolymer, that means single monomer usually is getting repeated. Polymerized each other, and then it forms homopolymer with macromolecule. And if we mix two different monomers, there is a high chances they mix at different manners. Say, for example, alternating manner, one next to another. Monomer 1 and monomer 2 and monomer 1 and monomer 2. And there are sometimes random arrangement, like kind of monomer 1, 2, and then two monomer. Monomer 1 will be occupied in the two. Repeating unit, and then again one repeating unit made up of monomer 2. Likewise, and then block type, like one monomer usually occupies 4 to 5 repeating unit, and the next 4 to 5 repeating unit will be occupied by normal. And we do have a craft copolymers, like the main chain is made up of monomer 1 and the side chain is usually made up of monomer 2. So like each has distinct characteristics and the properties, etc. Okay, and usually you get this kind of different types of, variant copolymer using different polymerization technique and different catalysts, etc. Okay, and which will lead to for the formation of different arrangement like alternative or the random or the graft or the black copolymer. So yeah, we'll study one by one, and I'll try to give you there itself some of the applications. I mean, why we are studying or why we are fabricating alternative copolymer and why we are studying random copolymer, etc. And then yeah, from the each content we'll be studying some case studies. We'll refer some of the research articles, and where you will have some clear idea. Okay. So I'm stopping here, and we'll see on tomorrow. I'm not taking, and can we have it on Thursday sometime? Thursday we have class, yeah, but slightly like I'll take 45 minutes or 50 minutes. So maybe